this point, you have been discussing linear collections. However, many applications require collections in which there is hierarchical relationship between items. In computer science, we call these collections trees. Now, these are hierarchical, and this means like they are characterized by the fact that each item can have multiple successors, and all items except a privileged item called the root have exactly one predecessor. So except for the root, they all have exactly one predecessor, meaning one parent, except for the root. Except for the root, meaning like the root will just have children, but it won't have anything that's its predecessor. It's the one that it's going to be starting out from. So for example, consider figure 11.1, which is the parse tree for the sentence. So the parse tree, like when parsing means like you break down a structure to its easier form. That's really what parsing means. Like you get a structure and you want to break it down and make it as simple as possible, trying to make that thing as simple as possible. So over here we have a sentence: the girl hit the ball with a bat. Now in this and in all diagrams of trees, the items are called nodes. The items that we're going to be, like, you can see that this example consists of a sentence. Now all of these words in the sentence are nodes. Trees are drawn with the root at the top, immediately below a node, and connected it to by lines and its successors or children. A node without children, in italics, is in the figure, is called a leaf. So a node without any kind of children is called a leaf. Immediately above a node is its predecessor or parent. Thus the root node sentence has two children but no parent. So could have two children, but it doesn't have any parents because it's a root. In contrast, the leaf node ball has a parent but no children. That's the definition of what a leaf node is. A node such as noun phrase that has children is called an interior node. Now, these are some of the fancy words or jargons you got to get used to. Now, here we have this parse tree. We had a sentence, and we broke it down into its noun phrase, verb phrase, or all of its parts of speech, what you could call it, right? So over here we have noun phrase, and you can see that noun phrase is broken up to article and noun, and then you can see, so this is basically the root, and then these are its children. You can see that there's two children over here, and then noun phrase has two more children, so you have two children here, and then you can see that the article has one children, the. So this doesn't have any children, so this is called a leaf node. Same as this is a leaf node, this is a leaf node, this over here is a leaf node, over here is a leaf node, here is a leaf node, you got one here, and you got here. And now the thing that is on top of it, this is called its predecessor. Now this predecessor has this other predecessor, so you could say that this is a parent and this is another. So these are like I would say grandparents of this child. So these all belong to it. Over here we have a book's table of contents is another familiar example of a hierarchical collection or tree. Here, however, each node is on a single line, and indentation indicates parent-child relationships. Not just these kind of figurine, which is basically a structure of a tree. This is how we represent a tree. Over here, it's in an indentation format, indicates parent-child relationship. The ellipses indicate omitted entries. Now, over here, the albatross book of living verse, and over here you see, this is, I would say, something like the chapter. Over here would have subtitles or subchapters. So early ballets of unknown date and authorship, and inside we'd have 3 sub chapters in this chapter. So over here we have this, and this, and then we have some things that are omitted. You can see that there's another chapter here. So this albatross book of living verse, this is the title of the book, and this has one child over here, another child over here, then we have one child over here, we have another child not here. So these are not children, but they're sub-children's. So we have these and this, and you could get by understanding that they're indented. Over here we have partial table of contents for the albatross, whatever it is. And then you can see, in addition, trees are used to organize a computer's file system, more related to computer systems, as we are reminded every time we view the files on our hard disk. So you can see that in a hard disk we have this kind of file system. There's an old interface of, I think so, Windows XP or earlier than that, where you have a file like a C drive, and then inside the C drive there's a couple of folders. Now you can see that some folders have subfolders and subfolders, and then there's internal folders in those folders. So that's how this tree is going to work: a partial directory tree of the files on the disorganized home computer of one of the authors. So this is basically a disorganized home computer of someone's, and it's just so many files inside of them. Let's talk about trees. So we have already introduced some of the terminology associated with trees, but there's more. The terminology is a peculiar mix of biological and genealogical and geometric terms. It provides a quick summary with the earlier terms repeated. So let's talk about the terminology of the trees. Over here, we're just going to go through, and we know that there's a node, and a node and an item stored in a tree. Pretty simple. Then there's a root, the topmost node in a tree. It is the only node without a predecessor. A child, a successor of a node. A node can have more than one child, and its children are viewed as organized in left to right order. The leftmost child is called the first child, and the rightmost is called the last child. Now we have here is parent. The parent, the predecessor of a node. A node can have only one parent. So the predecessor of a node is called a parent, and a node can only have one single parent. Now we have siblings, the children of a common parent. So we have, like over here in this example, these were siblings. Article and noun, siblings for noun phrase. So you can see that was like that. Edge branch, what is this? The line that connects a parent to its child. So we have those lines, those are called edge, or they're also called branches. These lines over here, they're all called edges or branches. And then we have descendant. So a node's descendants include its children, its children's children, and so on, down to the leaves. So all of the things that are on the bottom are called its descendants. Ancestors, our node's ancestors include its parent's parent, up to the root. Path, the sequence of edges that connects a node and one of its descendants. So the number of edges in a path is called the path length. So what is a leaf? A node that has no children. Interior node, a node that has at least one child. So what is an interior node? Which is a node that has at least one child, and then you have the thing on the top, so that's called an interior node. Over here we have a depth or level. The depth or level of a node equals the length of the path connecting it to the root. Thus the root depth of or level of the root is 0. Its children are level 1, and so on. So you can see that the depth of the root is 0. Over here it's 1. Over here is 1, 2. Over here it's 2, so this depth. And then over here it's 3, so this is getting 3. Then this is 4, and then this is 5. So this is like the depth. Alright, so depth or level. Height, the height of a tree equals the length of the longest path in the tree, or put differently, the maximum level number among leaves in the tree. So the height of that equal to the longest path in the tree. Subtree, the tree formed by considering a node and all its we exclude the root from forming subtrees. So like subtrees are like, you can see that there's a tree here that looks like a tree over here. Now we have number of nodes here, it's 10. You could count them: 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Height of it is 4. Now you can see over here 0, 1, 2, and 3. And when you count 0, 1, and 2, and 3, it's 4 basically. Root node is H. Leaves are this A, C, J, L, M, and N. Okay, interior nodes are this one, which has at least one child. So this one is H is an interior node. We have B as an interior node, F as an interior node, E as an interior node. H, B, F, and then we have E. Nodes at level 2. So we have 0, 1, 2. So nodes at level 2 is this, which have E, J, C, A. So A, C, J, E, correct? Ancestors of E. So we have E ancestors, which I would say F and H. So F and H are the ancestor descendants of F. So we have descendants of F here are J and E, and then we have JE and then LMN. Okay, what nodes in right subtree of F? So we have a left subtree and a right subtree. So over here we have an F, we have a left subtree which has just J node, and on the right subtree we have ELMN. So ELMN, a tree and some of its properties. Hopefully you got some clear understanding of how these trees are working. Now the trees have been discussing are we have been discussing are sometimes called general trees. The trees that have more than one, I would say more than two children. To distinguish between them from a special category called binary trees. In binary tree, each node has at most two children. So a binary tree is the tree that has children at most two. You can't have more than two. Two as the left child and the right child. So in a binary tree, when a node has only one child, we distinguish between it being as left and right child. Thus, two trees shown in figure 11.5 are not the same when considered as binary trees, although they are the same when considered as general trees. So you have A, B, C, and you could see over here that this one is basically two unequal binary trees that just happen to have equal set of nodes. So you have equal set of nodes, which are 4 and 4. Over here you have children B and D, and over here in the B section you have C. Over here you have A, we have B and D over here, and then we have C over here. They're both binary trees, but they're not the same.